Okay, so I do a survey of the paraconsistent program and its future. What I'm going to show you is something completely different from what João Marcos did. João Marcos was talking about the metaphysics of potatoes. I will be showing you some real French fries, some real baked potatoes, the real ones, not the metaphysical and very nice and very, how can I say, it's more analytic, right? I think he was going to agree with me. It has a very much analytical approach to it. I will be much more romantic, talking like Fernando Salamea like to say. I'll be much more romantic, trying to show some real applications. What I'm going to show you is what we have been doing here at the Center for Logic in Campinas since around 30 years ago. We have traditional 30 years of research. Okay, so my overview, we're going to be the following on paraconsistency again, very quickly, because João Marcos made that very clear for everyone, I suppose. Logical formal inconsistency, the same, he did already. Not about it, but I will show some real examples. Possible translation semantics and swap structure. That's something that João Marcos did not touch. And actually, it's very good that he's here because he's one of the major proposers of this possible translation semantic. He's one of the main players on this kind of thing. Marcelo Bonito and myself, we have been working on these swap structures that I show you what they are. Question of the algebraizability, and a new logic named RMBC, Marcelo here, and to correct me. First order NFIs, how quantifiers act under paraconsistent. They add quantifiers add a new level of difficulty, and it's possible to deal with them when they can do model theory. Everything you do is model theory. In classical logic, you can redo, you can regain in paraconsistent logic, but there is a cost, there is a price. New forms of set theory, new forms of probability and reference. Probability are my beloved topic nowadays. I am going to speak tomorrow, not tomorrow, because tomorrow we are going to this laboratory, but on Saturday, I'll be speaking only about probabilities and paraconsistency with new examples and everything. And reference. Okay, please interrupt me anytime, but not grumbling, please. I'm a little deaf, so I don't understand when people say, no way. And I don't see. Again, also I don't see, so I don't know if you are there. So I suppose there is someone speaking, okay? So please be kind to me. Consistency. So I like to recall this interview with Michael Dan, when he says, he tries, well, perhaps I don't read that, because you can read yourself. I suppose you can read well. Over there, I cannot, but I suppose you can do. But Michael Dan is telling something that is obvious, but it will require someone like João Michael Dan to say that to us, that the internet is a place for finding contradictions inevitable, right? Inevitable. So people used to say, oh, there are contradictions in databases, there are contradictions in daily life, there are contradictions in thought, there are contradictions in dreams. Yes, they are, but they are perhaps more than anything contradictions in the internet. Internet is full of possibilities for contradiction. So we really need paraconsistent logic as something real and practical for controlling information at the internet, right? Now, if there are real contradictions, as the dialecticians and my friend Graham Priest like to say, it's possible. I don't say that they are not. Who knows? In a planet, after the bang, a new Big Bang, I don't know what's going to happen. So it's very possible there may be contradictions in the real world, well, in the universe. But actually, we don't need them. We have already plenty of contradictions at the internet, right? In our dreams, in our thoughts, in our literature, in our poetry, and so on. So, Michael Dan, Belknap, they wrote a famous paper, I use it for verbal logic, and they are really talking about information in computer science. I remember years ago, I used to talk to Newton da Costa about possible applications of paraconsistency in computer science. And Newton told me sometimes, well, I cannot see why, because computer science uses recursive functions. Recursive functions are very clear, are very coherent. There are no contradictions in recursive functions. Okay? No, they are not. But there are contradictions in the application on what recursive functions talk about. Right? Subject matter of computer science is prone to contradiction. Okay. Now, in classical logic, as you know, we have contradiction and consistency and non-contradiction are equivalent notions, right? One of them requires the other one. That's the way you find in Hilbert, that's the way you find in Gödel, when he talks about the non-contradiction and consistency, they are the same. One of the most important points, I think João Martin made that clear, I'm not going to go on everything that again, but it's the distinction between contradiction and inconsistency. That's very much important. That's also our invention here at Center for Logic. João Marcos, Marcelo, and I, we invented that. Actually, João Marcos and I invented that before in a paper named Taxonomy of Systems, right? We came up with that idea that they are not necessarily the same. I mean, this is so important, this point, that if you understand that, you can go and have a beer. You don't need to stay here in the rest of my course. Really, this is very much important. Why is that so? I will be repeating that. But people don't pay attention. I will repeat again. Inconsistency is not the same as a contradiction. What is inconsistent? I repeat that story, but I start repeating now. Contradiction is when you say two different things. When I say A and not A. When I say this book is blue and this book is not blue. Inconsistent is something more general. It's when things don't go together very well. Like non-harmonic sounds. When you're playing piano, you have non-harmonic sounds. It's a kind of inconsistency. When you have something that's incongruent, incoherent, does not fit. This is an example of inconsistent, which is not contradictory, because contradiction involves language, like in Latin, contradiction. Say something again, say something to the contrary, okay? And this is very much important. I will be the basis of our work on paraconsistency nowadays. And this comes, for instance, information may come from multiple sources. And the sources themselves have some different degrees of confidence. I trust more. They say something different. I trust more in one than another. There is a search of inconsistency. What is the connection between inconsistency and contradiction? Very simple and clear. Contradictions are inconsistent. Inconsistent are not necessarily contradictions. Period. No more. Right? Now, you can make contradiction and inconsistency to be the same. You can. You add a new action that says contradiction is equivalent to inconsistency. You can add that. Then you are getting closer and closer to classical logic, but you don't need to. The most important point is that you don't need to buy that package. Right? The equivalence between contradictions and inconsistency. Okay. So we can somehow measure how hard the contradiction is by taking a certain degrees or probability. As we talked, Marcus mentioned that there's some way of controlling or measuring degrees of contradiction, degrees of inconsistent. There are many, many ways of doing that. One of the ways we do here is by means of probability, but I'll cover that in the next one. So, LFI, no, in classical logic, LFI, what are those LFI? Logic is of formal inconsistency. or perhaps they should be called logics of formal consistency. That should be perhaps a better name. They are logics where we take into consideration this distinction between contradiction and inconsistency, right? They take for sure this. I don't remember if João Marcos presented a system. You did it? Yeah, okay. So he did already. Classical logic can be regarded as a kind of LFI, a kind of logical formal inconsistency, when everything is taken to be consistent. Okay, so these LFIs, usually MCI or CI, there are many of them. They have this double personality. They are, on one hand, a subsystem. They can be regarded as a subsystem of classical logic, then they are subclassical logic, but at the same time, they can recover classical logic when you take for granted that any judgment, any proposition is taken to be consistent. Then if everything is consistent, the LFIs give you back the classical logic. So they are not any revolution. We are not cutting any part of the classical logic. We are just controlling them. It's just a logical control. That's what we do. Okay? So, there are infinity hierarchy of LFIs, from very, very basic to elaborate, like MVC, CI, CIL, CLI, blah, 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 the Costa system, CN. There is one logic that João Marcos mentioned en passant, perhaps you didn't pay attention to that. They said that, remember, C omega is not an LFI, right? It's not in the class of LFI, exactly. So the so-called limit, the Costa's limit of Cn, which he called C omega, is not the limit and is not an LFI. And they have a paper, João Marcos and I, where you show where the limit is. So unfortunately, some people, when talk about the Costa logic, go directly to the C omega, which is bad choice, to say this. Very bad choice. Okay. So there are many of them. You can invent many others. Some paraconsistent logic are many valued, like P1, J3, LFI1, which coincides with J3. J3 was studied by Professor D'Ottaviano and Professor da Costa years and years ago, more than 20 years ago. And you can think about 4 valued, 17 valued logics or whatever, right? So one important point here is that those logics belonging to this hierarchy, Da Costa's logic, MVC, CI, blah, 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 they can be proven to be non-characterizable by finite matrices. So, what's the relationship between paraconsistency and many-valuedness? The relationship is very open. Some paraconsistent logics are many-valued, some of them are not many-valued, some of them can be described in modal terms, as João Marcos mentioned, some of them cannot, and they can be first order, etc. Can be higher order, nobody studied that as far as I know. Higher order paraconsistent logic should be possible, it's not possible. Paraconsistent type theory is possible to do. Has anyone done that? I don't think so. Paraconsistent type theory would be a very nice topic because you could use them to make theorem provers or proof assistant, right? Like Lean, for instance, would be a very good candidate for working in paraconsistent type theory. That's my dream, but I don't have time to do it, or not having not yet. So what is the nature of contradiction that they are accepted in paraconsistent logic? So this is a very important point. This is what distinguishes our program from dialectics, right? So dialectics require or believe, I don't know if they require or they believe. I think that according to an explanation by Priest, they use paraconsistent logic because as they believe there are real contradictions in the world, the way to deal with them is by using paraconsistent logic. So paraconsistent logic to the dialectics is a tool. It's a tool that they are using, right? Because they found a stone which is square and round at the same time, or they believe they did. Okay? In our case, we don't need any stone like that. If we find it, okay, beautiful, it will be a very nice philosophical object to show with the television, a newspaper, blah, 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 but we don't need it. What we need, our way of the contradictions accepted in our program of paraconsistency are those that exist in language, in thought, in dreams, in expression, in information. You know, we are more prone, we're more close to the human contradiction, not to any metaphysical. That's a difference. That's a philosophical difference. Can paraconsistent logic be really useful? Well, they cannot be, as far as I know, they cannot be useful for mathematics. Mathematicians don't need it. And I know by experience, because in this room, I taught calculus 1, 2, 3, 4, linear algebra, blah, 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 during many years, exactly this room, because I was working in the mathematics department, and I was at the same time studying paraconsistent logic, and Professor Italy as well. We are teaching here for a long time. And we never found any example of any mathematical theory that needs paraconsistency. Never. You can invent one. You could. People have invented the topos, which are, they have a intuitionistic spirit. We tried, Marcetti and I and other people, we tried to find, to invent a mathematical object that would be behaving more like the anti-topos or dual of the topos theory. What kind of object would it be? A classifier of sub-objects, would it be completely different? We could not find anyone because mathematicians and mathematics, they do not need it. The only thing that I can remember or I can think that is more or less closer to a kind of a non-classical reasoning is topology, when they talk about the open set, closed set, and closed sets. It could be a kind of a three-value classification. But that's too little, and they don't care about that. They don't need the logic to talk about it. So mathematics do not need paraconsistent logic. Thus, physics need paraconsistent logic, very possibly. Where is my friend Idacio? He's there, he does not believe it. He thinks that the Schrödinger's cat is alive and dead at the same time. It doesn't require any paraconsistent. Is the cat escaping?
Yes.
But I disagree with him. I think that there can be any way of using paraconsistency in quantum mechanics. At least my student Juan Carlos Agudelo and I, we wrote a paper showing that we could propose a kind of paraconsistent Turing machine that's able to run quantum algorithms. So somehow, if not quantum mechanics, at least quantum cryptography or quantum computation could be close to paraconsistent law. Yes?
What about set theory? Couldn't it?
Yeah, we have, yes, okay, we have set theory. Marcelo and I have worked, and Newton Costa and Aida Ruda have worked in that kind of topic before. It's possible to formulate set theory, paraconsistent set theory, but the mathematicians don't need it. You know, that's for philosophical ground to take care of Russell's paradox and this kind of thing, right? What the mathematicians do when you talk to them about that, they say, I don't care. I mean, is Russell set dangerous? Don't talk about it.
Isn't that paraconsistent? Isn't that paraconsistent?
From their part?
It's not.
Yes, they can be, but they say, okay, so what? Let me do my theorem.
Okay.
So, there are no theorems that are not a theorem at the same time. You know? Theoremhood is classical. You cannot say, I have a theorem which is not a theorem.
So we have also developed a consistent
Calculus, yes, analysis.
analysis.
Yes.
Perhaps that's just because our meta theories are usually not consistent, even if we are talking about consistency.
That's a good explanation for psychoanalysis. No? Okay. They can be useful. I think they can. Nowadays, in the last 20 years, paraconsistent logic became very, very useful in computer science, in software, okay, in database. There they are completely because computer science needs it's not that they need, but they elaborate the work with the world as it is, and the world as we human people build it is prone to contradiction, right? So computer science really needs it. I in a recent project, I found at least 75 papers by people that were not in our group, right? That are using paraconsistent logic in for computer science for several other reasons, in ontology, in software verification, in proof theory. Alejandro Solares just finished a thesis on PhD thesis where he can agree with me, right? Anyway, so that's the real applications. So real applications are going to be in I believe in music, literature, software, computer science, poetry, cinema, not for mathematics, as far as I can. Yes.
I would like to press a bit more in his direction. Okay, maybe not in mathematics, but yes, in the philosophy of mathematics, in the rational reconstruction of what mathematicians are doing. So maybe even there it's...
Right. The Department of Mathematics do not have any chair named the philosophy of mathematics. You know what my teacher used to say to me? My teacher used to say to me when I was studying mathematics, I was making many questions, he said, please cross the street and go to the philosophy department. Ask them.
Professor, I'm sorry, but and I can say this because I'm a mathematician. It's not because most mathematicians are stupid that that's not mathematics.
We are not. I'm a mathematician myself. How can I say that? No, they are very clever. That's the point.
Well,
we
for
have
a long time, I think.
several no stupid mathematicians here.
And we are studying for consistency.
Yes.
So, for several centuries, people refused to believe in geometries that were not Euclidean.
Yeah.
That there's nothing to say that at some point we won't be thinking of mathematics paraconsistently. I can think of 2 examples of things in which my intuition says that perhaps we can find an inconsistency in mathematics, which is the field with one element. Every evidence points to its existence, but we can prove that it does not exist, so perhaps we could solve it with consistency. And then if you could do it, I'm hard-pressed to believe that not a single mathematician would accept it.
Very possibly. Well, it's not that mathematicians are stupid. So Cantor was intrigued by by behavior of this kind of not well. I'll be talking about that. Not well formed sets, etc. But when mathematicians try, Bombelli, Raffaello Bombelli, when he found this way of dealing with expression with imaginary numbers, he said, "Well, I would not like to deal with them, but I need them. Okay, so I do, right? But this is anyway. The best thing to solve this question is go and write a paper. Okay, leaving the burden of contradiction, I will be. Sometimes I talk too much and I skip my slides. That's my problem of a romantic way of speaking. Right? So, okay, principle of one important point is to keep in mind that paraconsistent logic, they have to do with rejection of the principle of explosion. right? It's just to, the trick is to control the power of the principle of the explosion. That's why João Marcos suggests that beautiful name of a gentle explosion. In paraconsistent logics, the bombs exploded gently, right? But, right? And gentle explosion, that was for sure. I think that
It's not
we had
the same
some
as kind explosion.
kind of explosion.
Not the same.
And then there's no much to do with the principle of non-contradiction. Some people make it wrongly, right? Principle of non-contradiction as in principle, I have to repeat the word. The principle of non-contradiction in principle has nothing to do with paraconsistent logic. Okay? What the important point is to control the principle of the explosion. Because then that's the real problem with classical logic. Is that in the presence of contradictions, everything gets trivial. So I deduce everything. What we human people never do. We never do that. Never, never. Not anyone you know, when found a contradiction, said, okay, the moon is a cube square. The moon is a Rubik cube in space, waiting for me to solve it. Or something like that, right? No way. So we human people have a very clever way of dealing with contradictions. When we find a contradiction, we revise it. We think what's wrong. We try to redo. So we just stop much before going to this step into triviality, right? So that's why. Paraconsistent logic is very close to human thinking, to human rationality. That's one point I'd like to emphasize. So, what paraconsistent is not? Paraconsistent is not the search for contradictions, neither the longing for contradictions. It's not that paraconsistent logicians look for contradictions. Like a vaccination does not look for disease. It's trying to control it. Right? Nobody takes, unless you are anti-vax, nobody takes a vaccine to be sick, to be ill, right? So, databases, especially big data and the World Wide Web, complex arguments, not only the World Wide Web, but complex arguments, debates, scientific measurements, etc., are almost inevitably contradictory, brilliantly contradictory. Okay? Paraconsistent then is a rational attitude of taking advantage of the contradiction rather than engaging in deductive suicide. Deductive suicide will be to deduce something from a contradiction which is completely stupid, right? So, but what do we gain and what is the price? So, then by studying, by doing paraconsistent logic in various guises, we gain some good points, we gain some good knowledge, but there's a price. I'm trying to show you now. What we gain was the price. So, the price we pay for proposing new logic is the following. We have to rebuild the logic without the principle of explosion. Right? You have to redo everything. You have to look for new definitions, new models. Marcelo and I, we suffer a lot for trying to find new models for algebraic models, models for paraconsistent set theory, etc., etc. It's not easy to find them. New decision procedures. Sometimes the decision procedure gets harder. If you think that by using paraconsistent logic you can solve P equals NP, you are completely wrong. Because it puts more gasoline in the fire. Right? New proof theory. We need new tableau, new kind of tableau, new kind of new rules. I mean, new everything. Everything new. So it's not inventing a logic. It's not only, okay, the logic says that and that, bye, 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 bye. No. You have to do everything in order to that your logical system get a citizenship, a logical citizenship. You have to find a proof theory, model theory, show completeness, blah, 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 blah. You have to show that this is as good as the old one. Right? So, the possible translations and semantic and swap structures is the following. Possible translation semantics is an attempt to offer a more generally acceptable philosophical interpretation for some non-classical logic, and especially for paraconsistent logic. So, Da Costa, when he invented his system, he had only a byte-valued semantics which could not explain anything. And I heard many times several people telling me, how can I use this in a computer? How can I explain your semantics for paraconsistent logic to an artificial intelligence, to an artificial agent? How can I explain this to an ET, an extraterrestrial alien? Right? So, my idea years ago was to think about what something later on was called a possible translation semantics. Where I show you what it is, and this is in master thesis by João Marcos, mainly. Then we introduced this in 1990, possible semantics. Now I introduced that before, and later much improved by João Marcos, Marcelo Cornilho, and myself. I'll give you some examples, starting from a basic paraconsistent logic, MBC. So what is MBC? It's just positive classical logic, which is assumed to be a reasonable basis, and some other very simple actions on top of it. So they work, possible translation semantics works by, I'll show you in a moment some drawings, some pictures that will make it that clear. By translating a complicated logic into a simpler one. In this way, a complex semantic behavior can be understood as an appropriate combination of other logics with simpler semantics. So Rosetta Stone, a paradigmatic case of several contexts, explains something complex. Again, João Marcos invented that story of the Rosetta Stone. I think he was in the British Museum and he saw that, and he got astonished by this. I tell you the story.
I actually invented before going there. I went there just to take a picture.
Ah, you went there to take a picture. I remember you had a T-shirt. Right? So I have a good memory. Yeah. So the Rosetta Stone were found by French soldiers in Russia, or Rosetta, close to Alexandria, is one of the most famous objects in the British Museum. But what is it? Well, the nice thing is, this Rosetta Stone, it had like 3 different levels or 3 different types of scripture: Demotic, Greek, and hieroglyphic. And someone, I think it was Champollion, had a nice idea of what nobody knew. How can you understand what hieroglyphs are? Right? There are some strange birds, some snakes, and what do they mean? Right? They had the wonderful idea of thinking about the following obvious idea. What if this stone is telling the same thing in 3 different languages? So I know Demotic, I know the Old Greek, blah blah blah. I know the other language more or less, but I don't know what's written in the hieroglyphic terms. So if I suppose it was a supposition, right? If I suppose they say the same, what would the hieroglyphs mean? And we sort of decipher it. And then compare this deciphering, the hieroglyphs, to other passages, other little fragments that people knew about old hieroglyphic scriptures, and they sort of were confirmed, they were coherent. So there is today, I would say, this understanding of the hieroglyphic language, or hieroglyphic science, is based upon an assumption. This assumption, the assumption that these texts say the same, right? Could be completely different. Very improbable, but could be. So, that idea that we are using in this possible translation is exactly that idea. We have a complex logic, which is not many-valued. I don't know what kind of semantics it has. But if you are able to decompose it into combinations of 3-valued or 4-valued simpler logics, then I have a different meaning. So it's like if someone is speaking a completely crazy language that nobody's understands, and then they put this guy here and you call some other people. Some call someone who speaks Farsi. Someone who speaks Yanomami language in the Indian, Yanomami, etc. And many people say, okay, I understand this sentence, I understand this word, I understand this term. And these people together is a possible translation semantic group. I mean, this speech of this strange language is being translated into several different directions, and the composition of them makes clear what the guy is saying. Only that, by working mathematically, we need to prove things. It's not just putting a guy there and asking some other people to sit in. It's not a round table, right? Philosophers do a round table, don't decide anything and move on. The mathematicians or logicians need to prove it, which is not easy. So, for instance, what happens in this complicated MBC, it is simple, but even so, non-finite valued logic. We have, for instance, we have an understanding of the conjunction, an understanding of the disjunction, an understanding of the implication, but 3 understanding of negation, and 3 understanding of this consistency operator. Eh? And then by translating, by changing the meaning of negation and consistency in a very clear and very clever mathematical way, we can prove the completeness of MBC by means of this possible translation. How can we do that? So, gamma, by means of this strange logic, entails phi if and only if the translations of gamma in these 3 valued matrices entails the translation of phi for every translation. Now, what are every translation? We have to clarify which proper translation have, and that's the hard part. So that's this. I think this drawing clarify everything. So multiple translating, you multiple translate it in order to understand it. So you have a strange logic, you translate it into L1, L2, L3, L4, blah, 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 and then you make a society of logics or a possible translation somewhere else. Formally, we have also worked on the idea of society semantics, which is quite close. It's more or less the same, not exactly the same. We don't know exactly what the relationship is. But, you can think like a society of the other logics which explain this strange one, okay, by means of translations. I have some additional material I distributed for you today. 2 kinds of additional material, two files. One file explains better what these possible translations are in terms of making more clear the mathematical treatment. And the other one is a file on something connected to this program here, talking about set theory, talking about other logic, blah, blah, blah. So I think they're a good material for you to start with references. Yes.
That's a nice question here. Just
Yes, please.
this might help. Just say what you wanted to ask. He was asking if it's bidirectional.
Yeah.
Then I said it's not. The translation.
No.
But one thing you could clarify is that each translation is sound. All of them together gives you completeness.
You know why they are not this arrow pointed here? Because I could not draw them. I tried during 2 hours how to put this arrow pointed there, couldn't I? But they are, yes, they're not bidirectional, they are sound. I mean, if you prove something here, then the translation proves some things there. Okay, so each one of them is sound, and the composition of them is complete. Beautiful idea, isn't it?
But the composition is not sound.
Hmm?
The composition is not sound.
Well, it's sound piece by piece. Our mathematicians say piecewise sound. Piecewise sound, right? But the clever idea, this is super, super clever. I mean, the combination of them gives you completeness. But I mean, real completeness, you can prove it. You have a proof that then you have a proof that something is true here, it's a tautology here, supposedly, if and only if it's a tautology in all others' understanding, all other translations, right? Now you can see can you would be, if tautology here, if it's, tautology in the majority of them, they would give you some different way of making, nobody did that, right? As far as I know. Talk about, instead of all of them, majority, for instance. Majority of translations or.
I did a little bit of this on the master thesis.
You did one,
With the society.
not majority. Yeah, society semantics
Showing
is.
that society
Yeah,
semantics is
yeah.
a particular case
Yeah.
of possible transcription.
But I mean, say like voting, like elections, majority, for instance, would be something different. Okay, I like this learning to reason from contradictions with Sherlock Holmes. Do not let the contradiction distract you, and truth will appear. So that's what Conan Doyle says in his little book, The Sign of Form. Eliminate all other factors, and the one which remains must be the truth. That's very human reasoning, very good human reasoning. That's what the judges do when they're judging a crime or something like that, right? You have lots of hypotheses which are conflicting. You get eliminated. You are not distracted by them. You are not deducing that the moon is a square cube. You're just trying to clean them one by one, making them rearranging them again, revising your belief, revising your deduction, revising your thought, and then you get to something which is close to the truth. If it's not the truth, it's very close. Okay? So, philosophically, this is the part of it. Swap structures, that's more complicated. But Marcelo is one of the chief masters of swap structures. We gave the name, and swap has to do because we swap positions with them. It's a little bit more complicated from the point of view mathematical, the combinatorics involved. So if you have a conjunction, disjunction, implication, 0, 1, be a Boolean algebra, you get a sort of 3 copies. Suppose you make 3 copies of this Boolean algebra, okay? It's a composition A times A times A, but with 2 addition operations. Then it's a kind of a Boolean algebra with operators. Boolean algebra with operators. You just require that this x1 or x2 is equal 1. I mean, these 2 guys here behave in the sense that they give you back kind of a tertium non datur, and you say that x1, n2, n3 is 0. So they cannot survive together. Okay? They cannot be together. So they makes a kind of bottom particle if you put them all together. Then this is a kind of a Boolean algebra with operator, but not exactly a Boolean algebra because it's a copy. It's a 3-stage copy. And then if you have a subset of this BA with multi-operations. Now, I'll show you what multi-operations are. Okay, I'll show you, I think an example makes it better. So the triples in the swap structure refer to truth values. For instance, this swap structure, it is treating phi, negation of phi, consistence of phi, and generating non-deterministic matrices. What is the trick here? The trick is, in Boolean algebra, you don't need any second component to talk about negation, because negation is determinate in Boolean algebra. Completely determinate. Consistency operator is always 1 in Boolean algebra, because everything is thought to be consistent. But here, we have to take into account this. Think about, for a moment, thinking these possible translations. You remember that which were complicated were the negation and consistency. We had 3 columns for negation, 3 columns for consistency. So negation and consistency are the problematic parts in the formal semantics of paraconsistent logic. Here again, we are dealing with phi, not phi, consistent phi. And these triples reflect it. Then based upon these triples, we make these non-deterministic methods for MVC. So, what's going to happen before I go further, let me just make clear one point. non-deterministic semantics are finite. And I said that MBC and many other paraconsistent logic do not have finite valued semantics. How is that possible? Because when I said that, I said deterministic. They do not have deterministic finite semantics. But the very nice point is that they can have non-deterministic finite semantics. And this is very nice because then we sort of get again this finite prospect with a kind of error, or a kind of error correcting code, in some sense, if you know that. Right? So what does this mean? I mean, the values are t, small t, t0, big F, F0. So it's degrees of the truth, degrees of falsity. And then when I get t, okay, so the distinguished values are t, small t, t0, non-distinguished F, F0. So when you get, for instance, the conjunction of big T and big T, this D here means you can choose any of the distinguished values. Okay? You have several different possible choices. Limited choices, but still with some freedom. For instance, F0 and T gives you something in the neighborhood of a non-deterministic value. So, non-deterministic functions are then mathematical objects. Right? They are very nice, but they are not completely determinate, but they are completely well defined. Right? And then by using that kind of thing, by using these swap structures, you can obtain a okay, so here I have this implication, negation. So you just have one negation and one operation for consistent, but they are non-deterministic. Which means you are recovering this degree of possible translations again. They are very close to possible translation, and they give then a 5 value non-deterministic matrix, which characterizes MBC. The method holds for many logics are formally inconsistent, and they are closely related to possible translation semantics. When you put new axioms to this MBC, you are able to redefine these from 5 values to 4 values, and then to 3 values, and then to 2 values. Then you are getting close. You are getting close classical logic again. Okay. So this is a very nice way. Then they can be very close. We don't know exactly if there is. Marcelo can help you here. If there is an exact morpheme between possible translation and swap structure, there's no any very, clear mathematical relationship. But we see intuitively that they are sort of. Yeah, they are perhaps more general, yes, and more prone to more. You can use computers here. You can use a computer to generate them, and very hard to use a computer to generate possible translations. They are weird objects. Anyway, there, these possible translations and the swap structures are 2 very nice methods to give formal semantics to these many valid logics. And you can sort of regain some algebraic components of a non-classical logic that were hidden, there. You can build a tableau. Alejandro, please. He's a kind of the king of tableau nowadays. I was before, but I gave you the crown. So we can make many other mathematical arrangements with these structures here. So it's clever. Yes.
Just a little addition, because you mentioned at the beginning decision procedures, which is probably what you have in mind when you mentioned putting in the.
Okay. Yeah.
But,
Thank you.
non-deterministic semantics might also be infinite. For instance, it's not by adding axioms that you're going to get values. So, for instance, if you do for C1, you cannot find a finite non-deterministic semantics or even swap, which is the same.
Yeah, that's true.
But the important thing is that you could still, in that case, Arnold has built that for the logic, to have infinite and still have a decision procedure.
Yeah. Well, that happens to S4 as well. Model logic, for instance. Yeah, so this here gives you a clear decision procedure, obvious decision procedure? What's the complexion of decision procedure? Do you gain anything by looking at it? No, it's worse. It's NP plus epsilon. NP complete plus something, right? So you don't make it, you don't make any progress in efficiency in computer science by looking at decision procedure for paraconsistent logic. Is it the same or worse? Possibly the same, because to be NP complete is already very hard.
And we then add that we have shown that if the induced proof theory associated to non-deterministic semantics can put in a certain format having a single consequence, then it's in P, not in NP.
Okay.
So there are cases in which you can.
Yeah, there are cases, yeah. But in general, you cannot say that in general you are going to make any substantial advancement. Yeah, in certain cases, yes. Like a subsystem of first order logic, it can be also P, can be a polynomial, right? In certain sense. Question of the algebraizability and the logic RMBC. Well, algebraizability is complicated for paraconsistent logics. It's a very hard problem. Why do we need the algebra in logic? Because we are used to look at logic and algebra as two sides of the same coin, right? We are sort of used to see Boolean algebra and propositional logic as the same, more or less. And the Stone representation theorem proves you that they are exactly the same, right, in a sense. Now, for first order classical logic, we also have these cylindric algebras, which are the counterpart of first order logic, and so on and so on. For modal logic, we have these Boolean algebra with operators, which give a way of attaching algebraic structures to modal logics, and then we go on. Finite many-valued logics are algebraizable. Professor Itala and Professor Mundici and Professor Roberto Signoli have a book on this explaining the complexity of many-valued algebras. They are not here to say that I can say bad things about it. It's a horrible book. Don't buy it. I mean, completely. No, nobody. So okay. So no, actually, it's a very nice book and shows you that if you have many-valued logics, you can find absolutely fine algebraic structures, but not for paraconsistent logics. They complicated everything. Why do they complicate? Because okay, let me talk a little bit about MBC. So it's positive classical logic by adding the following schema: A or not A, and this it was missing here. You see, when you write LaTeX, the stupid machines, they are not, the artificial intelligence is not able to reconstruct your missing sign. So it's consist of A implies negation of A, if everything together implies B for any B. This is the principle of gentle explosion or controlled explosion, right? MBC is a legitimate form of inconsistency, actually one of the simplest one. But then it suffers from the problem for replacement. What's the problem for replacement? Consider a replacement property, namely the following thing. If A is equivalent, alpha is equivalent to beta is a theorem, then I would like to, if I change B by alpha and B by beta, any other formula, also would get a theorem for every formula gamma which depends on beta, right? It's well known that MBC does not satisfy replacement in general. Just go here to the bottom of the slide. If A is equivalent, alpha is equivalent to beta, then not alpha is not generally equivalent to not beta. And A equivalent to beta, consistent of the alpha is not equivalent to consistent of beta. This simple problem destroys everything in algebra. Why is that so? Because in algebra, to make a Lindenbaum-Tarski algebra, which what we know how to do for most logics, you separate them in classes, right? So if A is equivalent to B, B, not A is equivalent to not B. And then you get the equivalent classes. If you don't have this property, you cannot do classes of equivalence. And the algebras work on the classes of equivalence. Algebra talking about equivalent classes. If you cannot do this in here, you cannot do any Lindenbaum-Tarski algebraizability, or algebraic, algebraic account. You cannot give an algebraic account to such logic. Okay, Lindenbaum-Tarski algebras are not the only way to assign algebraic counterpart to logics. You have Bloch-Pigozzi algebraizability. Still, you cannot do that here. There's a proof by Levine and Renato Levine and Anna, what's her name? Gloria Schwartz. Mickenberg and Gloria Schwartz that show that for most of, by simple examples, you cannot do a Bloch-Pigozzi algebraizability as well. So what should we do? Simple-minded idea. Just add those guys. Just add this here as new actions. And rules. As rules. Yeah, but then what? Then how can you change your logic? How can you get models for this logic? You might solve the algebraic problem, but destroy the logic. Right? So then comes the nice part. By adding this as new rules, so if A is alpha is equivalent to beta, not alpha is equivalent to not beta, and the same for consistency. In the logic, then we obtain the logic named R ABC. So ABC was replacement, right? Defined by this same signature and adding those rules. But then you have to rework the idea of deduction, right? Or derivation. A derivation of a formula in ABC is a finite sequence of formulas, phi1, phi(n), such that phi(n) is phi, and the last one, and the other ones are either phi or an instance of an axiom of RBC, or as a consequence of the other differential rules whose premises appear previously in the sequence. Okay, but then this is precisely the idea of deduction in modal logic. It's a kind of local deduction, it's not a global deduction, right? You have to change the definition. But if you change the definition of deduction and logic, you change everything. You change the spirit of this logic. And then you have to give, so you change this deduction definition, you have to find the semantics for this new logic. So the semantics is given by the suitable class of the Boolean algebra with addition operator. The semantic consequence relation, then, as I said, is degree preserving instead of truth preserving. It's a little bit technical. Degree preserving because, if something is less than one, then the consequence is also less than one. It's not truth, it's not preservation of the truth, but preservation of the degree of truth, in a certain sense. It's a little bit technical, but it's explained in these notes I sent to you. Then we define this Boolean algebra, this BALFIs, or Boolean algebra for NFIs. A Boolean algebra with NFI operators is then an algebra such that this part here is a Boolean algebra, the union operator satisfies A or not A1 and A not A is consistent with 0. Look, that is very much like to swap structures. The same intuition of structure. But here, in algebraic terms, in other kind of more general semantic terms. This BALFIs hold an interesting relation between non-normal model logics and particle system. Then we have, what we obtain here is a relationship with this new logic. Just by adding this operator, the new rules, we obtain a semantic is what gives us a connection to non-normal model logics. Okay. So the interesting point in this slide, I really don't like to read these slides, so that's why I put the slide and explain with my own words. What's interesting is that by using that kind of mechanism, we have been able to use this Isabel proof system to help us to find new models, to find new little theorems and so on and so on. Why? Because then we could make some hypotheses or some assumptions and ask Isabel to find a counter model or not, right? Yeah.
Because you have talked about consistency for software verification. So I was thinking because there are a lot of methods of private accounts that is related to some kind of computational logic, like intuitionist logic, by Corey Howard. I was wondering if there is some kind of relation between balanced logic and also some kind of computational calculus. You think that there is a relation?
There is a relation, but I don't know of any work in this direction. I mean, the same, kind of the Curry Howard isomorphism applied to paraconsistent logic, I don't know. Very possible there is, but I don't know. My people in computer science may help me.
I think that there is a book by Gavai and Quiros, that they are extending Corey Howard to non-classical logics.
Yeah, but not paraconsistent logic, are they?
I don't know, but probably by labeling or something like this.
Yeah.
I don't know.
Well, I think it is an open question. So, but we're not using a paraconsistent proof theorem or paraconsistent proof system. We were using this clear and classical Isabel proof system because all the meta theory is classical, right? Finding model or not finding model. Isabel is not quite never telling me there is a model which is a model and it's not a model. Meta theory is all about classical. We don't need, not even in intuitionistic logic. The meta logic is non-classical, as far as I know. And this is a problem for intuitionistic logic. So they'd like to have a yes.
I just want to
Yes, please, yes, please.
question.
Yes.
So the thing about lambda calculus is that the computational part of lambda calculus is consistent. So, I don't think that.
Yes, but I was thinking that that calculus that I was thinking needs to be consistent. I'm not talking about just the lambda calculus, but also more broadly.
Yeah, you're just in general inspired by that.
Yeah, I was thinking maybe computational have some kind of flaw like sources. So maybe a paraconsistent could help you to discover some kind of problem that they can describe algorithms that can fail and sometimes they don't need to be consistent. Maybe consistent. So I don't know if paraconsistent.
Yeah. I understand that it's not because it's a part of lambda calculus that is really about computation, is not the one that has inconsistency. So, but I understand you.
I don't know. That's an open problem, I think.
Question.
Oh, yes.
Related to those questions, I shortly listened to you and you talk about consistent Turing's. So maybe it is related to your questions. So may I know what those mechanisms?
Could be. So when we defined these paraconsistent Turing machines was to take some advantage of the superposition, quantum superposition, which is very much used in quantum algorithms. So we proved that by using these kind of new machines, which are not physically constructed yet, it's only theoretical machine, we could run some like Yosha algorithms and kind of, there are not many quantum algorithms, right? But yeah, and our intention was to try to use that machine to find new algorithms, which I could not find. But there are some relationship, but they're very vague for the moment. Then what happens is that this new logic is now axiomatized. It has a semantics. The semantics is connected to non-normal models of modal logic, right? So it makes paraconsistent logic closer to normal modal logic, because we already knew that paraconsistent logic, as Martin mentioned, is closer to modal logic in some sense, right? But here we gain some new connections to non-normal modal logics, and now our logic is fully algebraizable by Lindemann-Tarski algebra. And then what's the advantage of being algebraizable? Is that you can do, for instance, from my point of view, other points of view are possible. From my point of view, you can do directly probability based upon this kind of algebra, like we do with homography, right? The homography axioms for probability use start from Boolean algebra, the sigma algebra. So we can now think about a real sigma algebra, but a consistent sigma algebra of events. We can do that. We did not.
Can make a comment before you go into that, because you were mentioning the neighborhood frames. So the idea is that when you have replacement, that's what you need to get a neighborhood semantics for any logic. So replacement is what you need. You can write equations, and that doesn't give you
Is there a theorem in this direction, a general theorem?
Yes, any logic with
Ah,
replacement
okay.
has, I mean, Wojcicki proved in the book.
Okay, so we went to the right direction.
So, but then to get into normal modal logics, you have to add more. So what I presented was the logics with the reversal, the contraposition for the negations, and then you can get pre-key semantics, which is a particular case of neighborhood.
Yes. Yeah, but not in this case. I mean, we have to stop on
No,
normal.
it's more general.
Yeah.
But the other logics I presented before
Yeah,
were extensions of this, adding more things.
Yeah.
Like contraposition, which you like negation to.
But I think that here we're tight to this neighborhood semantics and non-normal model. I cannot do more than
It's a minimal extension, right?
Yeah. We could never add anything in direction to cryptic axioms, for instance. Cannot do. First order logic is how quantifiers act under paraconsistency. Let me go quickly. So, a first order version of each LFI starting from MDC can be obtained a natural way by adding to each system the following. So, you just add the quantifier, because quantifiers are quantifiers usually have nothing to do with negation. They are conjunctions, you can regard them as infinity conjunctions or infinity disjunctions, right? So in principle, you just add the same, I mean, this existence axiom, so AXT implies the existence. For every X, you can replace it for any term. Alpha implies any alpha prime is obtained by renaming boundary variables or deleting void quantifiers, blah, blah, blah. This is the algebra of quantifiers. I mean, there's nothing new here. The inference rules are also the same as very close to classical ones. So basically, if you have your proposition of paraconsistent logic, you add this machinery, then you are going to have a first order logic, first order paraconsistent logic. Now, the semantic is more complicated, right? The semantic is more complicated. You have to have a diagram language. You have to do a model theory with kind of care. It's a bit technically complicated. We have a paper on that. In the notes I gave to you, there are some references. They are little bit more complete explanation. Okay, but then you have to deal with some little bit different Tarskian structures, and then you get completeness, etc. Marcelo and I, with our students, to have a paper on expanded model theory. We were able to use them to obtain compactness theorem, to obtain a completeness theorem. What else? Lagrange column, upwards, downwards, right? What we did not try was to find, for instance, this joint consistency theorem, right? The joint consistency. model theory. That would be hard. Right? So there's still lots of work to do. If you get a good book on model theory, then you have their joint consistency, you have their Craig interpolation lemma for these logics and so on and so on. Right? We did not do that because actually it's still there waiting to be finished in this work. By the way, looking for good students who want to work on model theory of paraconsistent logic is first order. Right? If you like first order model theory, please talk to us. And by the way, we have grants. We received a big, good grant. Marcelo, congratulations. Juliana, congratulations as well. We have now grants for good students, good PhD, good postdoc students. And hard work. Okay, so this QMBC, quantified MBC, it has a, it's kind of close to first order valuation semantics, so it's the distinction that this here is not if and only if, it just implies implication on one direction, implication on the other direction, and the rest of them is more or less the same. But the fact that this one here is not if and only if makes everything much more complicated in order to build models, right? In order to build models, we suffer a little bit. Okay, I'm not going to go on that because let me see the time. Yeah, we have 15 minutes at most. Completeness, okay, it can be proved to be complete. It's important to note that in the paraconsistent framework, the notion of a non-contradictory theory is useless, since contradictory theories can be satisfied. So, this notion must be replaced by the notion of a non-trivial theory. These are the important points, are important methodological points in working in model theory or satisfiability or constructions of theory for paraconsistent logics in general. Like for model logic, Juliana did that in her PhD thesis and in papers. The notion of you have to use non-trivial theory instead of maximal consistency. If you want to remake or to rework with this, how do you call them? This canonical model theory, canonical models. You cannot use non-triviality. You have to use you cannot use consistency, you have to use triviality. Maximal non-trivial instead of maximal consistent. That's the turning point. That's the important point. If you understand that, you can make model theory for non-classical logic, for paraconsistent logic, much better, much more easily because you understood the points, right? You have to work on maximal non-trivial theory. Sometimes beta or alpha non-trivial means non-trivial respected to a certain given sentence, blah, 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 blah. So there's, right, Marcelo, would like to comment something on that? Okay. Marcelo did a lot of work with me on that. He worked night and day, right? To finish that really. So KBC is undecidable, of course, should be, as much as classical first order logic, but almost of a classical model theory can be reconstructed in QMBC, and the other quantified version of paraconsistent logic. That's the paper where Marcelo and myself and Rodrigo Podiatsky and Tarcísio Rodrigues, not to confuse with Abilio Rodrigues, Tarcísio is a student of ours, we published this paper to a wider model theory, completely steered for first order logics in the review of symbolic logic. But Arno Avron, Anna Zamansky had already worked on many valid non-deterministic semantics for first order logic of formal inconsistency, right? So they have another different approach by means of non-deterministic. Actually, we did not compare ours to theirs. I don't know what's exactly the difference there, but there are at least two different ways of new forms of set theory. Oh my goodness, it's going to be very hard to finish that. this. Okay, what we have here is we can build new theories that tolerate the Russell set. I mean, you can have R belongs to R and R does not belong to R at the same time without destroying the theory. And this is, and the way we did that, I show you very quickly. The way we did that, this is paraconsistent set theory. They existed before. So Newton da Costa had already proposed some forms of paraconsistent set theory. Some of them were shown to be incoherent, completely trivial, because they trivialized everything. Some of others are not. And Newton constructed a form of NBG set theory, blah, blah, blah. But then our intention was to redo this Z Zermelo-Fraenkel set theory. Simple Zermelo-Fraenkel set theory. The way we do that is the following. So we have this Leibniz axiom for equality, okay? X equals Y, then phi implies the changing variables. And the important part is this unextensionality axiom. Unextensionality axiom was saying the following: if X is not the same as Y, then there exists a Z, so that Z belongs to X and Z does not belong to Y. Or there exists a one Z so that Z belongs to Y and Z does not belong to X. So we, instead of having an axiom, using extensionality axiom, we have to make it the other way around. An extensionality axiom, right? Because of the complications of negation. But the most important parts is the following. We add a consistent operation on sets, which is not the same as the consistent operator for sentences. So sentences can be consistent or not, and sets can be consistent or not. That's why I think they can be, my conjecture, I could be wrong, you say I'm wrong, they can be close to quasi-sets. That's the conjecture. Right? So, the axiom said the following: for every X, X belongs to Y. If X is a consistent set, this implies that Y is a consistent set. So, if X is a consistent set, the assertion, the judgment about the equality of them behaves very well. See quantum ideas around here. Right? So the identity is only well behaved if you have if they are elements of a consistent set. See, that's the problem of identity in quantum mechanics. And now, for every X, if it's not the case that the identity is well behaved, then X is not a well behaved, a well determined set. Right? Now, with this simple thing here, after some 38 pages of work, we prove the following. This theory is as good as ZF. It's equiconsistent with ZF. As you know, we cannot prove that ZF is consistent, right? Only believe it. Do we have a proof of the new proof?
I just want to have a question. How do we know that consistent set exists? Should we put it as an axiom, like an empty set?
I'm sorry, but I could not hear you.
Consistent sets exist.
What is?
Consistent sets exist because in C1 up to C4 we have just conditions. How should they behave? So shouldn't we say that there exists at least one consistent set?
Yeah.
That's what he asked.
He gave that.
No, I think we have to. We don't even have to say that there's an infinity consistent set.
Sets constructed by using classical connected, because this logic contains classical.
Yeah.
Then Zermelo-Fraenkel contains it. Then the empty set constructed by using the classical negation, that if this does this has no element, that no is classical one, not a consistent negation, then that set you prove to be consistent.
Okay, so it's a theorem then.
Yeah.
Okay.
Okay. Now, what's important here is that this theory is exactly consistent with that. So, if ZF is destroyed, this one is destroyed as well, and vice versa, right? So it is completely well done from the point of view of mathematics. Yeah, please.
In what sense are they equiconsistent? I mean, how is
If this one is trivial, the other one is trivial.
okay.
That one does too, because in mathematics you also use the action of choice. So you have something about the action of choice also.
Yeah, you can formulate the action of choice. What we do not have is any proof that the action of choice is independent. We don't have that. To do that proof, we started working on forcing. But you need new kinds of force, still no problem. Huh? Okay, so what is a set to be consistent? Actually, this is a kind of a primary notion. We don't know what is a consistent set. It's a well-formed, mathematically well-formed, right? What's an age well-formed dream? I don't know, but some dreams are well-formed, some others are not. So, intuitively, this we found some Cantor talking about inconsistent sets as well. We tried to rescue George Cantor's idea, as well as Hadamard and Jourdan, on inconsistent set in his mathematical reasoning, where contradictions were regarded as beneficial. So what Cantor says in a letter to Dedicate, a collection, Vielheit, because this Vielheit, what's Vielheit? Manifold. I mean, how? Vielheit can be so constituted that the assumption of a unification of all the elements, making them as they call a Menge set, right? Unification of the element into a whole leads to a contradiction, so that it's impossible to conceive of the collection as a unity, as a completed of them. Such collections I call absolute infinity or inconsistent collections, not well-formed collections, not well-formed Vielheits. But besides having that, what he, taking his inconsistent sets into account, Cantor concluded that every consistent set had to be power equivalent to a definite aleph. So that's what Darwin says. In one theorem, based on the inconsistency of the system of all transfinite numbers, Cantor had succeeded in resolving several perplexing and long-standing problems in set theory, like to attach a definite aleph to any of those field height, even if they are not well behaved, even they are not so Cantor, I think you would sort of agree with our set theory. I hope, I suppose. Yeah.
In that set theory, do you have unlimited comprehension?
No.
No. I mean, can you prove the existence of an inconsistent set?
Yes, Brussels set.
How do you construct it without unlimited comprehension?
I don't remember now. We don't need it.
Huh?
Just comprehension.
The empty set defined
Yeah.
by a consistent negation.
Ah.
Equal and different.
Yeah.
Okay, you have both negations.
Yes.
Okay.
No, we can use anyone you like, yes. We have defined another one. Well, question, yes. I am sorry because I cannot hear you using masks. I can hardly see that you are there.
Wasn't Cantor's word for set Manifoldkeit? So how do you know that when he's talking about Vielheit here, that he's referring to the same thing?
There were two terms, Vielheit and Manifoldkeit. Are they the same? He asked. Manifoldkeit and Vielheit.
No.
Well,
I cannot.
then how do we know that Cantor's really like? Because then the motivation is lost there because Cantor's term for set was Manifoldkeit.
Well, this is an analogy. I cannot say that we are using, because after ZF was being constructed by Zermelo Frankel, there's no more inconsistent field heights. They are what they have in classes maybe, but not inconsistent field heights. We're just coming back to the history and trying to rescue some of the old ideas, but we, as mathematically, we cannot do that. I don't think so.
So maybe it's just the difference between collection and set. It's not exactly the same.
Collection and what?
Set.
Set is main good.
Yeah. I mean, now in contemporary set theory, what you have? Sets and classes, right? But the Cantor was before.
He invented main good.
Yeah, he invented that. So we are trying to. I mean, Cantor was a genius, and if he says that inconsistent field heights can be useful, I cannot applaud him and say we are closing his spirit, because Zermelo Frankel set theory is not for sure the only way to axiomatize or to make clear what Cantor had in mind. We possibly have another way of materializing what Cantor had in mind.
Okay, well, but still, you shouldn't use set. Right? You say inconsistent set, he's not using main good, not set. It's something else. Collection. Keep using collection.
Families, collection, Menge, I
It's
don't know.
not a set. Not for, even for Cantor. It's not set.
Yeah. So how can I say let's construct a new Menge theory?
You said collection.
Yeah. Okay,
Stick to it, don't say inconsistent set.
Can be. Well, the paper is published, anyone can write a criticism, it would be very welcome. But okay, this is not a propaganda, this is just for you to know, absolutely not a propaganda, as ceci n'est pas une pipe. Well, that's not a real propaganda, because we are not making money on this.
No one can buy it.
Huh?
Because no one can afford buying it.
I tell you a secret. Do you need to buy books? So, that's why this is not a real propaganda for making any money. This is a propaganda on the academic level for you to know that there exists a book which by that time was figuring 25 years of consistency at Unicamp with many subjects inside of it. And it's a worth. It's worth its value. It's a worth reading. It's a worth carrying it on your suitcase.
But consistently exists because you cannot produce a copy. You cannot find it.
I have a copy myself. So models for set theory, one hard problem, I'm going very quickly here, is to find good models for paraconsistent theory. So Marcelo and I will have a more recent paper on this logic and logical philosophy, where we show some ways of constructing, starting from a tree-value perspective, how you can build some models for set theory, but it's a complicated thing. We cannot, I mean, you cannot do, suppose V equals L, for instance. How can you make that kind of assumption here using this particle system? How can you do the lots of thousands of results you have in set theory? How can you regain them here? I don't know how. It's very difficult. It's okay. So what we have there, models generalizing the ones by Benedict Leuwe and Tarafder. I don't remember his first name. Suraf Tarafder. He was here. This guy was here in Campinas with us. And open possibilities for independent results on the paraconsistent set theory. So, again, nobody could find a nice proof of independence either for the action of choice nor for generalized continual hypothesis using that kind of models or Taraf there or Leuven models. Or, anyway, this is a completely open problem. Would be very nice. Or otherwise, I mean, suppose you can prove that a action of choice in this formulation here can be derived. That would be a nice value, extremely nice value. Contrary to this tradition of independence, it started by Coyle, right? Or Coyle. Okay, new forms of probability. That's what I will be talking on Saturday on my last class. I'll go very quickly here on them. We have a new logic, name it logic of evidence. Huh?
Please, sorry, are you finishing?
Yes and no. Huh?
Yeah, because
What do you prefer, no or yes?
this part for Saturday.
Yeah, let me just go to the last one where I say thank you for it.
If possible, we need some more minutes.
Too many questions. I'm sorry. Anyway, I'll be talking on Saturday in more terms of this paraconsistent logic and probability, what I think is something very astonishing. It's very much interesting. Just to show you, what you have here is this sum of probability of alpha and negation of the alpha can be bigger than 1 or less than 1. This is sufficient to change everything, okay? So, new perspective in Ghetto completeness. I also have here, I have a two-page paper where I'm showing the connections with Ghetto, even and paraconsistent, and that's all I had for today. Thank you very much.